Hey class, hope everything is going well this week with our dynamics, something that we looked at in grade 11 quite a bit. A good chunk of grade 11 is looking at dynamics and forces and how they work. We're going to smash kind of the first 2 or 3 weeks of dynamics into 1 week here. So let's look at this. So here's our dynamic formulas are just basically these two very simple formulas. Force equals mass and acceleration, and then we bring in our frictional force. So force friction equals mu times force normal. Those are kind of our only two formulas here. Now we add in basically angles and inclined planes to kind of bring in the vectors and make sure that we split it up properly. And we can bring in either other forces, like in the sense of someone is pulling on it. So we have again, another force in another direction. So that's where we have to bring in our net forces. But basically, these are our only two formulas that we kind of have here. So the one thing that we do, though, in grade 12, with a lot of our content, not just dynamics, but with all the work going forward, is we like to make it like what we call whole problems, in the sense of, I'm going to bring kinematics into dynamics. And going forward, when we start over, like after spring break, we're going to be starting to work on work and energy. When I start with work and energy, some kinematics and dynamics will make its way into there too. When we start working at rotational, so circular motion, we're going to start putting torque, and then yes, kinematics. And so everything is going to kind of keep building on each other. We're not going to just forget about kinematics. And then when we're done dynamics, we're not just going to forget about dynamics. They're all going to kind of work hand in hand quite often as we go through this. It's just a big area of what we call mechanics, okay? So let's go through some examples where they kind of go hand in hand. And I'm going to look at questions 7 and 8 on the practice sheet for frictional forces. So that's question 7 and 8 I'm going to go over today, as well as I'm going to go over question, I think, 6 at the forces of angles. That might be another little separate video, just question 6. So in this one, I'll just go through questions 7 and 8 on here, and that'll be looking at, again, how do we tie in dynamics and kinematics together. So let's go through that. Okay, question 7 here. Let's write down all my variables as we go. So it says a car with a mass of 1,200 kilograms, okay? It's moving at a speed of 80 kilometers. Now, honestly, anytime I see, unless we're trying to figure out like the time in hours, which we're probably not doing, I like to change this to meters per second right away. So velocity equals 22.2. How do I get that? Anytime you have kilometers per hour, divide it by 3.6, not 36, 3.6, and that'll give you your meters per second. So if you go 80 divided by 3.6, that'll give you 22 meters per second. All right. It says the mu, your coefficient of friction, is 0.80. So that your coefficient of friction is 0.80. Determine, I want to know eventually, way down here, the time. The time it takes to actually stop and slam on the brakes, okay? So, like I said, kinematics and dynamics are going to overlap. They really only overlap with one singular thing, and that's this, the acceleration. We have a lot of acceleration in here, and we do have a nice little acceleration in our forces formula there. So that's usually what's going to tie everything between. Either I can find an acceleration from the forces and then try and put it into kinematics, or I can try and find acceleration from the kinematics and then figure out the force afterwards. So question 7, we're going to start down here and then figure here. In question 8, we're going to start here and then bring it over here. All right, question 7 here. So I have a mass, which means I can automatically find force of gravity. Force normal is going to be the same here as well. So 1,200 times 9.8 gives me 11,760. Same with force normal. There's no angles here, so they're exactly the same. No one else is pulling up or down on it, so exactly the same. Newton's. Now I can take that force normal. I have my mu. I have my coefficient of friction. I can find how much friction force there is. Friction force. Well, let's put the mu first. 0.8 times 11,760 gives the answer of 9,408. So that is my friction force. And actually, that's my only force. This car is trying to brake. So the friction force of the tires is the only thing that's acting on it. I mean, besides force, normal force, gravity, they cancel out. There's no other force, so that is the net force. That is the net force that's me going to put into here. Okay? So now that I have that, I can find my acceleration. Acceleration equals force divided by mass. So 9,408 divided by 1,200. I get an acceleration of negative 7.4884. Oh yeah, meters per second squared. So I have an acceleration now. I'm going to write that in a different color. That's the time. The acceleration is always the time. Negative 7.84. All right. So now that we have that, we can kind of flip the page. We've done the dynamic side. We can kind of pull in the actual kinematic side. So I'm going to erase this for now. All right, so we have this acceleration. Like we have basically this car. Again, it has a velocity of 22.2, and it is going to move and eventually come to a stop, which means VF is 0. And the nice thing is we figured out this actual acceleration now. And what are we looking for? We're looking for a time. How long does it take to stop? Okay, so if we look at my kinematics formulas now, we have a VI, we have a VF, we have an acceleration. We can figure out that time using our first formula. That acceleration equals VF minus VI over T. So negative 7.84 equals, again, negative, 0 minus 22.2. Time, switch these. So time will equal negative 7.84. Oh, my bad. Negative 22 over negative 7.84. Okay? And so now that you got that, time equals, what do I got? 2.83 seconds. 2.83 seconds. All right, so cool. So that's how long it will take this car to stop. We've found out the actual frictional force, which told us the acceleration. Once we knew the acceleration, we could figure out how much time it took to stop. So that's how we can kinetize it. I'm going to turn my light back on and come back. All right, so there's question 7. Let's go to question 8, where we're going to take a dynamics part. A kinematics part, and then tie it into dynamics. All right, question 8. There we go. It says an NHL hockey puck weighs about a mass of 0.16. It is shot from one side of the rink to the other side and 60 meters away. Distance equals 60 meters. It begins traveling at 15 meters per second, so VI, 15 meters per second. Across the ice and hits the other side 4.6 seconds later. So I have a time of 4.5 seconds. Seems like I have a lot of kinematics things here. Okay? Determine the coefficient of friction. Okay. So again, what do I need here? I need, what's the thing that always binds these two sides? It's the acceleration. So first off, I'm going to have to figure out an acceleration. I don't have enough down here because I don't really have any forces yet. I don't really have that. So let's kind of look at my kinetic side. Can I get an acceleration? Figure out my kinetic side. I have a distance, I have a VI, I have a T. And the nice thing is I can use this formula, okay, to figure out my acceleration. So let's try and do that. I have my distance, which is 60, equals 15. Okay, time was 4.5 seconds. Plus 1/2, I don't my acceleration, then 4.5 squared. Cool. Where was my calculator? There's my calculator. This one I didn't do fully before. That's okay, I was going to do it with you guys. So 15 times 4.5, I get 60. 7.5 plus, again, what's 4.5 squared? I'll do that part. 4.5 squared, 20.25. So 1/2 a 20.25. All right, so let's move this over. I still have 60 here. If I move this over, so minus 67.5 minus 67.5. I get negative 7.5 equals 1/2 a 20.25. All right, so if I do just like times this by 2, again, a half times it by 2, so I get negative 15 plus a and 20.25. Let's divide 20.25 by 20.25. Please be right here. I get an acceleration of 0.74, which is right. So negative 0.74. Okay, so that's my acceleration. Okay, obviously this puck slowed down. All right, it didn't keep going the same exact velocity the whole time. I got a acceleration of negative 0.74. All right, I can use that now. I can use that over here to figure out my force. Again, if a puck's sliding on ice, it's probably the only force that's acting on it is just friction. Okay, so I'm going to kind of get rid of our kinematics side. Go to my dynamics side. I know acceleration. Negative 0.74. All right, can I find my net force? Do I know what the net force acting on this was? Well, I know my acceleration. I know my mass. I was given that. So let's find the net force. Net force equals 0.16 times 0.74. Okay, which gives me a force of 0.118. Okay, there's a frictional force of 0.118, which I know is not very big, but when you're talking about a puck, still something. All right, and now the nice thing is, now that I know that the frictional force is kind of the only thing that's acting on it, that is my my net force is my frictional force. So now that I have that, I can use my net, my force normal, which is just mass times 9.8, to figure out this mu. So let's go 0.16 times 9.8. I get force normal equals, where is force normal? 1.57, 1.57. And cool, I can actually figure this out. Okay, mu is going to equal force of friction over force normal, which means I get 0.118 over 1.57, and I get a mu of 0.075. So 0.075 is my mu. All right, so kind of again, this is what we're going to do a lot more in grade 12 is we're going to learn something and we're going to see how it can attach again to whole problems, because these are problems that we like to basically figure out. Maybe not the puck one so much, but especially the car dynamics and forces that start with kinematics. If I need to know a force, how fast is it going to move me, how long will it take to get there, all those things start tying together. Okay? I'll have one more video about question 6, about the forces and angles and how I can, again, tie in these dynamics and kinematics, and that'll be my last video. All right, thanks class. Let's do this. And we're good. All right, perfect.